So let's look at the applications of Laplace transforms, which make it such a powerful tool in many areas of mathematics and beyond. These include ordinary differential equations, partial differential equations, integral equations, and so on. So let me go through them one by one. So the first one is linear ordinary differential equations. Differential equations, in short ODEs. So for example, an example of a linear ordinary differential equation is y prime minus y equals 0. So this is a first order ordinary differential equation. You can also have y prime plus a y prime, y double prime plus a y prime plus y equals some function of t such as t squared. So here y of course is a function of t, y is a function of t, and y prime is the derivative of y, and y double prime is the second derivative of y, and so on. So these are examples of linear ordinary differential equations, and we have seen how to take the Laplace transforms of first derivative and higher derivatives. So we will use that method repeatedly to solve such equations. Second is linear partial differential equations. In short PDEs. So for example, say y is a function of t and x, then you can have an equation such as del y over del t equals del 2y over del x squared. So this is a partial differential equation which is second order in x and first order in y. So the Laplace transform technique can also handle such partial differential equations. Third is systems of ordinary differential equations, linear ordinary differential equations. For example, if you have functions y1 and y2 unknown functions, then you can have equations such as y1 prime equals y2 plus y1 and y2 prime equals minus 3y1. So this kind of system of, so this is a system of ordinary differential, linear ordinary differential equation in two unknowns, and each unknown appears in the first order differential equation for each derivative y1 and y2. So the Laplace transform technique can help us to solve such problems as well. Fourth is integral equations. Just as the derivative of an unknown appears in the differential equation, an integral of an unknown, when it appears in an equation and we have to solve it for the unknown which is an integrand inside the integral, then it is known as an integral equation. So for example you have y is a function of t, then y equals integral 0 to y yu over square root of t minus u du, and you have to solve for the unknown y, unknown function y. So this is the kind of integral equation where the unknown function appears inside the integral and as well as outside the integral. So the Laplace transform technique can help us here because we have integrals from 0 to t, and we know what kind of Laplace transforms these integrals have, and it can also handle things when you have such type of convolution equations. In this case, in this example, we have a convolution equation which is y star of the function 1 over square root of t, and so we know from the convolution theorem what kind of Laplace transform it may have, and so in this case one uses the Laplace transform to solve these integral equations. Now you can have a mixture of integrals and differentials. So let me write this as integro differential equations. So these are equations where the unknown appears both as a derivative as well as inside an integral. So for example, so y is a function of yt, an unknown function, and the equation can be of the form y prime plus ay equals integral 0 to t tyu du uyu du. So the unknown appears as a derivative even without the derivative and even inside an integral. So again one can use Laplace transforms. Using the basic properties of Laplace transforms that we know about, we can solve such equations. Then we have difference equations. Difference equations. So here y is a function of unknown function of t, and you can have an equation of the form y t minus 2 plus y t minus 3 equals y t minus 1. So here t is taken to be greater than 3 if y is defined only for positive t, then you have to consider positive values of y, or you can also impose the condition that yt is equal to 0 for t less than 0, and then you can solve equations which now involve the second translation theorem, because you can write this as in a particular form which will be amenable to our second translation theorem. So these are called difference equations, and a related type of equation to solve is called recurrence relation, where you have a sequence of unknown numbers a n. These are all unknown, but they follow a known pattern of equations such as a n equals a n minus 1 plus a n minus 2. So one can solve such equations. These two are interrelated. Difference equations and recurrence relations are interrelated, and they can be solved using basically the same method. And so we will look at these two types of equations, solving them by the use of Laplace transforms. And lastly, you can have miscellaneous types, miscellaneous equations, where you have mixtures of equations of the above examples. So for example, you can have a differential equation which is so for example given by y t minus 1 equals y double prime t. So you have both the difference aspect for the difference equation as well as the derivative aspect for the differential equation, and these are known as differential equation. Similarly, you can have difference integral equations, as well as you can have equations where all kinds of types appear. For example, you can have a difference term, you can have an integral term, you can have as well a derivative term. So the Laplace transform technique takes care of all these kinds of equations. Using just the basic knowledge of Laplace transforms, you can solve these kinds of equations, and this makes the Laplace transform a very powerful tool in many different subjects, because all these types of equations are used to model real world phenomena. So let me write this as a remark. All these kinds of equations are used in mathematics and other physical sciences such as physics, chemistry, etc. You can also have economics, and these kinds of equations appear quite frequently in trying to model real world phenomena, and as well as in engineering subjects. So engineering subjects. So for example, if you have electrical circuit in electrical engineering, electrical circuits, so these can be modeled by integral differential equations. You can have bending of beams problems, bending of beams in mechanical engineering, etc. So all these kinds of differential equations, integral differential equations, integral equations, difference equations, and so on, they can be used to model real world phenomena, and so the Laplace transform makes it it gives you a very powerful tool to solve such kinds of equations. So let's begin our journey for applications. So the first one is linear ordinary differential equations, linear ODEs. So in this course we will look at only a few specific types of linear ODEs. So they can be broadly divided into two groups. So one is initial value problems, where you have given values for some initial conditions. So initial conditions for the unknown y, unknown function y, are given at a specific point t equal to a. So you can have a equal to 0, for example, and so these are called initial value problems. Then you can have boundary value problems, where y is thought of, yt is a function which can be thought of for values of t lie between 2 points a and b, and these are the boundary for the domain of y, and conditions for y are given at t equal to a and t equal to b. So these are called boundary value problems. So we will look at both these kinds of equations. Let us begin with a very general type of initial value problem, which is these are called initial value problems with constant coefficients. So these are linear ordinary differential equations of the form yn plus alpha 1 y n minus 1 plus alpha 2 y n minus 2 plus up to a constant term, say alpha n y plus some other constant beta equals some function f of t and valid for t greater than or equal to 0. And the initial value problem, in the initial value problem you will have the values of y0 equals c1, y prime 0 equals c2, y double prime 0 equals c3, and so on up to the n minus first derivative evaluated at 0. All these values cn minus 1, these are given. So then the initial value problems with constant coefficients can be solved using the Laplace transform technique as follows. So we can take the Laplace transform on both sides of this equation. So we will get, so take Laplace transform on both sides, and let us denote the Laplace transform of yt as capital Ys and Laplace transform of the function ft as capital Fs. So of course ft is a given function here, and all these alpha 1, alpha 2, alpha n are and beta are also given. So this and all these coefficients as well as this function ft, these are also given. So our when you take the Laplace transform, our function fs, capital Fs is known. So this is known, and you have to find ys. So the idea is to apply Laplace transform on both sides. So using the fact that the Laplace transform for the nth derivative is equal to, so we assume that the hypothesis for the derivative and higher derivative theorems apply for y, which means that y is assumed to be piecewise continuous, and all derivatives up to n minus 1 are also considered piecewise continuous on the whole interval from 0 to infinity, and the derivative, the nth derivative also exists as a piecewise continuous function. So then we can apply our derivative theorem. So you will get snys minus sn minus 1, the value at y0, minus sn minus 2 y prime 0, and so on, and in the end you will have the n minus first derivative of y at 0. So these values are all given. Recall that these values have been given as c1, c2, c3, cn minus 1. So you will get Sn times Ys minus C1 Sn minus 1 minus C2 Sn minus 2 and so on minus Cn minus 1. On the other hand, you have for each derivative such an expression. So therefore our transformed equation, so this is called the transformed equations when you take the Laplace transform on both sides. transformed equation will have some form, something like Sn plus k1 Sn minus 1 plus k2 Sn minus 2 plus up to some constant kn times ys. Note that this ys will have many different powers of s coming from the various different derivatives of y by the derivative theorem for higher derivatives, and so it will there will be many such powers of s, but in general it will be some polynomial in s. So this is a polynomial in s, so we will denote it as qs. This is a polynomial in s, and then you will have is equal to some function ps, and on the right hand side you will have the Laplace transform for this function f, and then there will be other terms which come from the left hand side, which will be a polynomial ps. This is again a polynomial in s, and so now we have to solve for ys. So now the problem is reduced to an algebraic equation. So the transformed equation is always, this is an algebraic equation. So we started with a differential equation, and now we have an algebraic equation. The Laplace transform has given us an algebraic equation from a differential equation, a linear ODE, and so we can solve for ys, which is fs plus ps over qs. And so if we can find the inverse of this function on the right, then we have solved the problem. So which means that yt is the inverse Laplace transform of fs plus ps over qs. So we will see that in many cases we can solve it quite explicitly, and here since we have one of our terms is ps over qs, then the method of partial fractions will come in quite handy. Partial fractions is very important tool to solve such equations. So let's look at an example to illustrate this method. So suppose that I take y triple prime minus y equals 1 plus t squared, and given the initial values y0, y prime 0 and y double prime 0, so their initial values will be up to the second derivative because we have a third derivative in the differential equation. So these are all given to be 0 for simplicity. So now let's take the transformed equation, and this is given by s cube ys. So because all these other terms are 0, you will only get, this is the Laplace transform of the triple derivative of y, all other terms will be 0, and then the second term is simply ys, and then on the right hand side you have 1 over s plus 2 over s cube. So therefore you can write that, solve for ys, and you get s square plus 2 over s cube minus 1 times s cube. So now we can use various kinds of methods to solve for the inverse Laplace transform. So I am going to use the method of partial fractions. partial fractions method. So we will write s square plus 2 over, I am going to write s cube minus 1 as s minus 1 times s square plus s plus 1, and then you have another s cube term. So we have a repeated linear factor here, one linear factor here and one quadratic factor here. So we will have a1 over s plus a2 over s plus a3 over s, second one is s square, third one is s cube. Then you have for the quadratic factor b s plus c over s square plus s plus 1, and then you have the linear factor d over s minus 1. So let us see an example which illustrates this method. So let me take the differential equation y double prime minus y equals 1 plus t square, and I am going to take the initial values all 0, these are 0. So note that here the initial values will be up to the first derivative because we have a second order differential equation. So then taking the transformed equation gives you s squared ys. So here again ys is our Laplace transform of yt. The other terms will be 0 because we have both y0 and y prime 0 are 0. So s square ys minus ys equals 1 over s plus 2 over s cube. So ys is 1 over s times s square minus 1 plus 2 over s cube times s square minus 1. So this is s square plus 2 over s cube times s square minus 1, and you can write it as s square plus 2 over s cube times s minus 1 and multiplied by s plus 1. So you have, this is a repeated linear factor and these are linear factors. So you can use the method of partial fractions to solve for ys. So ys can be written as a1 over s plus a2 over s square plus a3 over s cube plus b1 over s minus 1 plus b2 over s plus 1. Now if we solve this, so on the left hand side you have s square plus 2 over s cube times s minus 1 times s plus 1, and so solving this one gets the following answers. So a1 equals minus 3, a2 is 0, a3 is minus 2, and b1 and b2 are 3 by 2. So this implies that ys is minus 3 by s minus 2 over s square plus 3 by 2 1 over s minus 1 plus 1 over s plus 1. So this is minus 3 over s minus 2 over s square plus 3 by 2, and you have 2s over s square minus 1. So this 2 cancels out, so you have this term is 3s over s square minus 1. So now you can invert this easily. You will get minus 3 minus 2t plus 3 times cos hyperbolic of t, and this is valid for t greater than or equal to 0. So one should check that this is the right answer. This gives you the solution yt. So our general method can be summarized. So let me summarize the general method. To summarize, this method is to solve an initial value problem for an linear ODE. So you start with an ODE, linear ODE with given initial conditions. For example, you can take our solved problem y double prime minus y equals 1 plus t square, and then you can apply the Laplace transform on both sides, and you will get an algebraic equation in S variable with unknown ys. Then you can solve for ys. You can solve this algebraic equation for ys. So in this case, in our example, our ys was s square plus 2 over s cube. Well, you had an equation of this form, and then you can solve for ys. Solve for ys, and you get simply s square plus 2 over s cube times s square minus 1, and then you can invert this using the inverse Laplace transform to get the solution yt of our equation 1. So the Laplace transform technique gives you a somewhat easier method. Then you can also apply for other methods. The Laplace transform technique gives you an easier method to solve the differential equation, which can also be solved using other methods to find the solution. But here, since we are solving an algebraic equation and then inverting this, in many examples, this other method is actually using the Laplace transforms is actually simpler than other general methods to solve differential equations that we learned.